time for a change, we're going to talk about Stern Gerlach and spin. Now, spin will keep us busy the biggest chunk of this semester. So it will be spin 1/2, and we're really going to go into enormous detail on it. So this is just the beginning of the story that will be elaborated at various stages. So at this moment, I will do this, talk about this experiment that led to the discovery of spin, and what, if you try to invent a theory that describes this experiment, what you would possibly begin doing. And then we go through the mathematics, as I mentioned to you, for maybe a week and a half or 2 weeks, and then return to the spin with more tools to understand it well. So the subject is the Stern Gerlach experiment. Stern Gerlach experiment. So the Stern Gerlach experiment was done in Frankfurt, 1922. It was an experiment that, in fact, people were extraordinarily confused. Was not clear why they were doing it. And for quite a while, people didn't understand what they were getting what was happening with it. In fact, Pauli had thought that the electron has like 2 degrees of freedom and didn't know what it was, those 2 degrees of freedom. Kronig suggested that it had to do somehow with the rotation of the electron. Now, Pauli said that's nonsense. How can an electron rotate and have angular momentum because it has a rotation? It would have to rotate so fast, even faster than the speed of light, to have the angular momentum, and then this little ball that would be the electron would disintegrate, and it made no sense to him that there would be such a thing. So Kronig didn't publish this. Then there were another 2 people, Uhlenbeck and Goldsmith, at the same time, around 1925, had the same idea, angular momentum of this particle. And their advisor was Ehrenfest, and said, doesn't make too much sense, but you should publish it. And thanks to their publishing, they are given credit for discovering the spin of the electron, and Pauli, a couple of years later, decided, after all, I was wrong. Yes, it is spin, and it's all working out. And 1927, 5 years after the experiment, basically, people understood what was going on. So what were these people trying to do? First, Stern and Gerlach were atomic physicists, and they were just interested in measuring speeds of thermal motion of ions. So they would send beams of these ions and try and put magnetic fields and deflect them and measure their velocities. And eventually they were experts doing this kind of thing, and they heard of Bohr that said that the electron has angular momentum when is going around the proton in circles, so it might have angular momentum. And said, oh, if it has angular momentum because it's going around the proton, maybe we can detect it. And when they did the experiment, they got something, and they thought, well, we're seeing it. But it was not that. They were not seeing the orbital angular momentum of the electron, because that electron in these silver atoms actually has no angular momentum, as we will see, no orbital angular momentum. It only has spin. So they were actually seeing the spin. So it was a big confusion. It took some time. Basically, they took the beam and they split it with a magnetic field, and the clean split was something nobody understood, so they called it space quantization. As of, it's separated in space. Space is quantized. a pretty awful name, of course. There's nothing quantized about space here, but it reflects that when you don't know what's really happening, your names don't come out too well. So what we have to understand here, our goal today is to just see what's happening in that experiment, quantify a bit the results, and then extract the quantum mechanical lessons from it. So let us begin with the important thing. You don't see the spin directly. What you see is magnetic moments. So what's that? So what are magnetic moments? Magnetic moments mu is the analog, the magnetic analog of an electric dipole. A mu is called a magnetic dipole. You say it has a magnetic moment. And the magnetic moment is given by I times the area. What does that mean? Well, a precise discussion would take some time, but roughly, you can simplify when you think of a loop that is in a plane, in which case there's an area associated to it. And if the loop is this one, the area is defined as the normal vector to the oriented loop. So an oriented loop has an area vector. And the orientation could be thought as the direction of the current. There's an area, and the magnetic moment is given by this thing. It points up in the circumstances when this current goes like that. So that's a magnetic moment. A little bit of units. The way units work out is that mu b, magnetic moments like magnetic fields, have units of energy. So magnetic moments you could define as energy, which is joules, divided by Tesla, or ergs divided by Gauss, because mu b has units of energy. So how do magnetic moments originate in a charge configuration? Well, you can simply have a little current like that, but let's consider a different situation in which you have a ring of charge of some radius r. It has a total charge q. It has a linear charge density lambda. It's uniform. And it's rotating with some velocity v. If you wish, it also has a mass, m. All kinds of parameters. How many? Mass, charge, radius, and velocity. Here we go. We have our solid ring of charge rotating. And we want to figure out something quite fundamental, which is the origin of this principle. We said you really never see spins directly. You never see this intrinsic angular momentum directly. You see magnetic moments. But then, actually, what happens is that there's a universal relation between magnetic moments and angular momentum. This is a key concept in physics. Maybe you've seen it before, maybe you haven't. Probably you might have seen that in 802. So how does that go? Let's calculate the magnetic moment. So the current is the linear charge density times the velocity. The linear charge density is the total charge divided by 2 pi r times the velocity. Now the area, to give the magnetic moment, we have mu is equal I times area, so it would be this q times 2 pi r, v times the area, which would be pi r squared. So the pi's cancel, and we get 1/2 Q V R. Okay, 1/2 QVR, and that's fine and interesting, but okay, depends on the radius, depends on the velocity. So here is the magnetic moment is supposed to be going up, but what else is going up? The angular momentum of this thing is also going up. So what is the magnitude of the angular momentum L? L is angular momentum. Well, it's the mass times the momentum. No, it's the mass, momentum cross r, so mvr. The momentum of r cross p for each piece contributes the same, so you just take the total momentum, that is really 0, but add them up little by little, and you've got your mvr. So here you have VR. So here you put 1/2 Q over M, mVR. And you discover that mu is equal 1/2 Q over M L. So maybe write it better, Q over 2M L. And I box this, I'm sorry, this is the normal, the M shouldn't change, M. And I box this relation because interesting thing has happened. All kind of incidentals have dropped out, like the velocity has dropped out. The radius has dropped out as well. So if I have one ring with this radius and another ring with a bigger radius, the relation between mu and L is the same, as long as it's rotating with the same speed. So this is actually a universal relation. It's not just true for a little ring. It's true for a solid sphere or any solid object axially symmetric. It would be true. You could consider any object that is axially symmetric, and then you start considering all the little rings that it can be built, and for every ring, mu over L is the same, and they all point in the same direction. Therefore, it's true under very general grounds. And that is a very famous relation.